Yeah, thank you very much. First of all, I'd like to thank the organizers for having me. So I'm Teruaki Suyama from Institute of Science Tokyo, and my topic is primordial black holes. So let me start. So recently, primordial black holes are getting more popular and popular. So I guess many of you here may have heard about the primordial black holes. But just for completeness, let me use this slide to explain the motivation to consider primordial black holes. So primordial black holes are hypothetical black holes produced in the our universe. And the original theoretical idea of the theoretical possibility of the primordial black holes dates back to early 70s, where it was proposed that when the large density perturbations in the our universe directly collapse into the primordial black holes. And since then, even nowadays, this direct collapse from the large amplitude of the primordial density perturbation is, I think, the most standard and most popular formation mechanism of the primordial black holes. But since then, there are many, some other formation mechanism of the primordial black holes have been proposed, like cosmic strings, bubbles, or domain walls, etc. And the important feature of the primordial black hole is that this mass, contrary to the stellar mass, contrary to the astrophysical black holes, which come from the collapse of the normal star, of which there is a lower limit on the black hole mass. The PBH mass can be much smaller than the solar mass or much greater than the solar mass. And if we consider this direct collapse of the primordial density perturbation, which is the most standard one, then there's a simple, so those black holes are formed when the size of the density perturbation becomes comparable to the Hubble horizon at the initial time. Then we can roughly estimate the PBH mass to the horizon radius at the time. And this is the relation between PBH mass and the formation time. So if you want to produce like a stellar mass primordial black holes, then the formation time is this 0.1 millisecond, right? Which is the age of the, this is really the right after the beginning of the universe. And why I say hypothetical, or why there are so many, why there's so variety of the primordial black holes is basically that we don't know nothing about our universe. So many cosmologists believe that there was a period of inflationary stage in our universe where universe expands rapidly, and the primordial density perturbations are created out of the quantum fluctuations, and the inflationary universe transitioned into the radiation-dominated universe. We are sure that this happened, but when you ask more, what is inflation, inflaton? Is there, what's the shape of the potential, or single field, multiple fields, or how the inflaton decays into radiation? What's the reheating temperature? We know nothing about this. And and because of this, there are many inflationary models. And some inflationary models predict primordial black holes whose mass is greater than solar mass. And some inflation models predict the primordial black holes much smaller than the solar mass. Some inflationary models predict no production of the primordial black holes. So if we are able to probe observationally the primordial black holes, that can tell us give the useful information of our universe. So that's one of the motivation to consider, motivation from cosmology to consider primordial black holes. Sorry, I spent too much time only for this slide. So this is a current constraint, observational constraint on the abundance of the primordial black holes, and the vertical axis is the so-called F fraction of the primordial black holes in terms of the dark matter. So 1 means 100% dark matter is primordial black hole, and as a function of the PBH mass. And you see there's a window where primordial black holes can be 100% dark matter. So, okay, so this is just the upper limit on the abundance of the primordial black holes, but this is not the, having the upper limit is important, but this is not the end of the story. And exciting thing is that we might have already detected primordial black holes, but we are just not sure that the detected signals are coming from the primordial black holes. And today I'm going to cover two such possibilities. One is the black holes detected by LBK gravitational wave events. So the target black hole mass is a stellar mass. And the other is, as I said, the dark matter. And as I showed in the previous slide, the remaining window is like asteroid mass range, 10 to minus 16 solar mass to 10 to minus 10 solar mass. So I am going to address these two different topics one by one. So the first LBK gravitational wave events. So it's known that so primordial black holes are, as I said, produced in the very, very early universe. And at the formation time, their primordial black holes are distributed, isolated. So each black holes are like an isolated black hole. But as the universe expands, the primordial black holes starts to come in within the Hubble horizon, and they start to interact by the gravitational interaction. And some of the primordial black holes form binaries. And in the last 10 years, some people investigated intensively this formation rate of the binaries and the merger rate of the binaries. And this is, I think, the most recent merger rate as a function of this fraction FPBH. So this is 100% dark matter, and so this, and there are a couple of different physical processes for the mergers. And so in this figure, 4 different processes are shown here. And this is this dotted horizontal line is the upper limit set by the LBK collaboration. And as you can see, the LBK gravitational events are consistent with PBH mergers in the sense that the PBHs can explain LBK upper limit for FPBH less than 1. So if the required value of FPBH is greater than 1, this is inconsistent. By definition, FPBH must be less than 1. So this is so this shows that the PBH can be one scenario to explain the LBK data. So but we know that astrophysics also produce stellar mass black holes. So the important question to ask is how can we distinguish PBHs from astrophysical black holes? And there could be multiple ways to address this question. But I think the simple and easy to understand answer, the observable is the redshift evolution of the merger rate. Here, I plot the merger rate, redshift evolution of the merger rate normalized by today's merger rate. And this blue curve is a merger rate when the FPBH is 0.1, which is somewhat disfavored already by LBK observations. But anyway, so this is a merger rate when FPBH is 0.1. And the orange one is the merger rate when FPBH is 10 to minus 3. And this green curve is just a star formation rate, which is like expected when you assume that the margin black holes are astrophysical black holes. And it's not necessarily that the astrophysical merger rate completely trace the star formation rate. So here I cite one of the paper which did more astrophysical computations to compute the merger rate. And this curve is slightly different from this green one, but there's a but it's clear that the merger rate traces the star formation rate. And what we can see from here, the general trend is that the astrophysical merger rate of the astrophysical black holes, initially at low redshift, it increases, but beyond some redshift, like 2 or 3, merger rate decreases. On the other hand, the primordial black hole merger rate monotonically increases towards a higher redshift. So this is a clear distinction. So if we are able to measure this merger rate, redshift evolution of the merger rate, we may be able to distinguish PBHs from astrophysical black holes. But in the figure I shown in this previous slide, there was no the contribution from the first stars, I mean the POP3 stars, were not included. So you may ask, POP3 stars are like formed at higher redshift, and they may contribute significantly, which may contaminate the merger rate from the PBH perspective. So this is a paper which did a computation of the merger rate even towards the higher redshift. And this red curve is a merger rate of the POP3 black holes, and this black curve is a merger rate of the primordial black holes. And if we include the POP3 contribution, then the merger rate continues to increase towards up to like a redshift 10. But beyond the redshift 10, even the POP3 merger rate starts to decay. So if we are able to measure the merger rate beyond redshift 10, and if we find that the merger rate shows the monotonically increase toward the higher redshift, this may be regarded as a smoking gun of the primordial black holes. I thought this is a smoking gun, this could be the smoking gun, but the first talk of today's session says that the astrophysics beyond redshift 10 and the astrophysics at the lower redshift may be totally different. So even if we detect this behavior of the merger rate, maybe this can be explained by astrophysical processes. So that's the reason why I put the question mark right after your talk. Yeah. But apart from this uncertainty, suppose this is a correct prediction, then we have to wait for a long time to get a good detector which can probe redshift beyond 10. But this is like, in principle, we can answer. If we wait for, I don't know, 10 years or 20 years, I don't know, but if we wait for a long time to have a good detector, this can be answered. So, yes. So, yeah. But maybe we are not, we cannot wait for such a long time. Then maybe we can partially address this question. And I think so I consider this extreme case where all LVK events detected so far, like 200 or 300, I don't know. But all LVK events are caused by primordial black holes. This is like an extreme case, and I think not too many people are seriously considering this case. But the question I'd like to ask is that, is a possibility that all LVK events are caused by PBHs already ruled out? And how much is it unlikely? And maybe this can be addressed by looking at this merger rate at low redshift. So for instance, redshift between 0 and 1, there's a PBH merger rate depends on the FPBH, but this dependence only appears at higher redshift. So this, there's a almost unique prediction of the merger rate, redshift evolution of the PBH merger rate at redshift like between 0 and 1. And this slope, yeah, sorry, I will finish in a few minutes. So this slope is clearly different from this slope of the astrophysical merger rate. So if we can precisely measure the this slope, then we can say that so if the measured slope is robustly different from this slope, we can robustly say that this possibility is ruled out. Sorry, I have prepared this lensing and the dark matter. I thought I could talk everything in 15 minutes, but sorry, I already used 15 minutes. So let me stop here. Yeah, so this is a summary. Thank you.
Okay, Teruaki, for this very clear and nice talk. Perhaps you could come back to the other points in the discussion session. Yes. Any questions? First Prasad and then Ish and then Patrick.
Yeah. So you are mainly saying that by seeing the way the merger rate is there for PBH and the astrophysical black holes, we can differentiate. But in case we start detecting both of them mixed together, so it will be very difficult to detect, right? And also, why I'm just wondering that if the primordial black holes are very smaller, mainly you may see them as stochastic background, not as isolated events. So can you comment on this too?
Yeah, thank you. So if the among the LVK merger events like 200 or 300, if the PBH, suppose they exist, but if the PBH constitute only a fraction of the observed events, then so if the astrophysical black holes are dominant component, then the merger rate will be close to this redshift evolution of the merger rate will be close to this green one. So yeah, in that case, it's quite difficult to like extract, pick up the primordial black hole contribution. So we should look for other observables. But what I wanted to point out here is that before going into this possibility of the mixture of astrophysical and primordial black holes, the first question is the first question we can answer is this extreme case. And as far as I know, this question has been, many people will think that this is very unlikely, but this is, I think, a first person perspective or subjective point. So I want to know, so but just by using the data, can we, from the present data, can we exclude the possibility that all LVK events are primordial black holes? And in that case, this redshift evolution of the merger rate may be useful. Yeah, that's what I want to say here.
Thank you for the good talk. So just about this question itself, I know of a paper from some years ago that used some spin statistic and Hawking entropy arguments to say that if primordial black holes were to exist, the population should have had a natal spin of 0. So they should be non-spinning. So firstly, could you create spinning black holes that are primordial? And if you cannot, then that basically answers that question, because with LVK, we have seen spinning black holes. So they must not then be primordial.
About the spin, I'm not sure if we have a definite conclusion or definite prediction on the spin of the primordial black holes. Initially, like 10 years ago, people, cosmologists naively expected that because the primordial black holes are formed out of the very nearly spherical overdensity, so the spin is quite small. But after the discovery of this LVK events, people consider various possibilities like a formation of the PBH in the early matter-dominated era, in which case the PBH have very large spin. So yes, so I think a spin can be like a useful quantity, but so as far as I understand, there's no definite prediction of the spin distribution of primordial black holes.
Last question by Patrick.
What a comprehensive talk. My question was concerning the LVK mass spectrum, where you have a narrow peak at 10 solar mass and a broad peak around 35 to 40 solar mass.
Yeah.
So where does the primordial black hole mass spectrum, how does it compare with that from various theoretical models?
Yeah, so that's a very important question. As I said at the beginning of this slide, there are many inflationary models. And so there is no definite prediction on the mass distribution of primordial black holes. So now we have this very complicated feature of the observed mass spectrum. I think in principle, it's possible to explain this invent inflationary models, inflationary potentials to realize such complicated features of the mass spectrum.
Thank you, Teruaki, for this nice talk.